All right, Theorem 17 states this. If two triangles have two sides of one equal respectively to two sides of the other, and the included angles are unequal, then the triangle, which has the greater included angle, has the greater third side. So in essence, what we're saying is if two sides over here in this triangle equal two sides respectively to another triangle, and they have two angles that are not equal to each other, that are in between these two equal sides, two pairs of equal sides, then the one that has the greater included angle will have the greater third side. So in this case, I said that angle C is greater than angle F, which should state, or we should come to the same conclusion that this theorem says that AB will be greater than DE. And so that's what we're trying to prove. We have triangles ABC and DEF, where AC equals DF and BC equals EF. I've already placed those first things in the proof here. And then step 2 and 3, statement 2 and 3, are kind of, if you're new to geometry, might be a little confusing. But we can use move through space kind of ideas to help us prove things. We don't usually have to move through space a whole lot, but sometimes you need to. And in this case, that's what I chose to do here, move through space. And so what I said in statement number 2 was place triangle DEF on top of triangle ABC, so that F, it's over here, I've already stated that we're going to put F right on C, and that FD will fall along CA. And so if you kind of can't see with your imagination or pretty much picture it in your brain, this is what we're doing. If I were to pick up this triangle and move it on over here and put point F of that triangle right on point C, then we would see that FD would also fall along CA. And so that's what we are saying here. And as you saw also, step number 3 was true. Since these are equal line segments, D will fall on A when we do that. So that's what I said for statement number 3. D falls on A because of the definition of equal line segments. Their endpoints are able to be made to coincide. And so we were able to move this triangle because you can move any geometric figure through space without changing its shape or size. And none of its properties have to be changed when you move a geometric figure. And so there is the first 3 steps there. I'm going to now say that since we said in statement 3 that D falls on A, this is now also D, and I'm going to just draw the remaining lines here to move our triangle over. This is point E, so now I have the same triangle that I had from over here. All right, I'm also going to move these marks because this is EF here, and it was equal to BC, so that side is still equal. We haven't changed its properties. And I don't know if you can see it, but we almost have an isosceles triangle. We just need this side right there. So that's going to be my next step. I'm going to say draw EB, because 2 points determine a straight line. 2 points determine a straight line. So let's draw and connect E to B. All right, now we have an isosceles triangle. I'm going to zoom in, and I'm going to label some angles here. 1, 2, 3. Kind of small, but I think that will work. And since this is an isosceles triangle here, we know things about the base angles of an isosceles triangle. Angle B, this big angle out here, not angle 1 by itself, but the entire angle B, is equal to angle 2 here. They are both the base angles of this isosceles triangle. So we can say in step number 5, statement 5, that angle B equals angle 2, because we can state that angles that are opposite equal sides in a triangle are equal. All right, perfect. Number 6. We're going to now state some relationships between bigger angles and smaller angles. So let's zoom on in here again, and we can see that angle 1 is smaller than angle B because it's part of angle B. And so we could say it the opposite way. We can say that angle B is bigger than angle 1. So that's what we're going to say here. Angle B is greater than angle 1. And we can say the same thing about angle E and 2. Angle 2 is smaller than the big angle that it's a part of. Angle E is also greater, we could say, than angle 2. So I'm going to say that angle E is greater than angle 2. And we can say that because we've learned this, that the whole is greater than any of its parts. There we go. Number 7. We can now state this with the information we have stated in our proof. We can now say that this angle, this base angle of the isosceles triangle, is greater than angle 1, which is part of the other base angle. We've already stated that these two angles are equal, and so if this is smaller than that, then this has to be bigger than the part. So angle 2 is greater than angle 1. Angle 2 is greater than angle 1. And we can use the substitution axiom because we've already stated the relationships between those two angles. All right, and then number 8, we can now say that angle E is greater than angle 1, 2. We can say that angle E is greater than angle 1. Number 8, because, and I'm going to really abbreviate it, but I'll talk us through it. If the first quantity is greater than, and I don't even say that, greater than a second quantity, and a second quantity is greater than a third quantity, then the first is greater than the third. So this is what we've said. We've said that these two are equal. We've said that this is greater than that. We said that this is greater than that. So this is greater than that. All right, so there we go. And now we're just focusing on this small triangle down below, this one right here. And we have angles that can tell us about the sides of the triangle. We've learned in Theorem 14 that sides that are opposite bigger angles in a triangle are bigger than sides that are opposite of smaller angles. And so we can now say that AB is bigger than what would that be? DE, because of that theorem we've learned. So now we can say what we've set out to prove. We can state that, and I need to go down a line here, number 9, we can say that AB is greater than DE, because if one angle of a triangle is greater than a second angle, then the side opposite the first angle is greater than, I don't need to say that, greater than the side opposite the second angle. And again, that was Theorem 14 that we learned that idea. And so there we go. We just proved Theorem 17, stating that if we have two sides in one triangle equal respectively to two sides of another triangle, and the included angles between them are unequal, well then the triangle that has the greater included angle will have the greater third side. Theorem 17. Okay, and then we have Theorem 18. And you can see that this is the converse of Theorem 17. This says that if two triangles have two sides of one equal respectively to two sides of the other, and the third sides are unequal, then the triangle with the greater third side has the greater angle opposite that third side. And so that theorem that we just covered, theorem 17, stated we have two equal sides of one equal respectively to two equal sides of the other, and the included angles were unequal, and whichever angle was bigger, it would have the greater third side. Here, we're stating the opposite. We're saying that the third sides are unequal, and whichever one has the greater third side will have the greater opposite angle. All right, so we said angle C and angle Z were unequal. This was bigger than that, which made this side bigger than that side. Now we're saying these sides are unequal, and since this is bigger than that, we're stating that angle is bigger than that angle. Okay, we're not going to do a direct proof here. We're going to do an indirect proof. And I listed out all the possibilities. We're trying to prove again that angle C is greater than angle Z because AB has been stated in the given to be greater than XY. So whichever side is greater will have the greater opposite angle. So we're trying to prove these angles are unequal and that angle C is greater than angle Z. So that's our first possibility. The only other two possibilities that we're going to look at, and that really could be the case, is they're either equal to each other or angle C is less than or smaller than angle Z. Well, now let's just quickly take a look at it. It won't take very long. If angle C, we're going to put this aside again, and we're going to try to prove that these are correct. And if there's any contradictions with the given, then they can't be correct. If angle C equaled angle Z, so if I said that angle C equals angle Z, then we've got a problem here, because if these are equal to each other, then we have one side equal respectively to another side, an angle equal respectively to an angle, and another side equal to another side of the triangle respectively. And we would have something called side, angle, side. These two triangles would be congruent by side, angle, side, which would mean that AB would equal XY. There's our contradiction. We are told already in the given that AB is greater than XY, that it does not equal XY. And these would have to be equal by corresponding parts of congruent triangles to be are equal if these are congruent triangles. So that is out of the picture. Now, if angle C was less than or smaller than angle Z, then we would have what we just learned in theorem 17. If this was smaller than angle Z, then we'd have a smaller side over here than over here. If this was true, then we would have AB smaller or less than XY. But again, our given was stating that AB is bigger than XY, not smaller. So again, there's another contradiction, and a very quick indirect proof. We can see that this is the only possibility, and that would prove that this theorem is stating a true fact, that the converse of theorem 17 is also true, and we call it theorem 18. So theorem 17, theorem 18, there it is.